The first thing to mention for these motion problems to remember is, now we've already got, okay, yes, life was easy as pie until high school. Ha, ha, what a pun. Okay, so, all right, what was I saying? Okay, the first thing is that when you are given a position equation, you can take the derivative of your position equation. Remember that that gives you a velocity equation, and that the derivative of velocity becomes an acceleration equation. And you can integrate an acceleration function to get a velocity function. And when you integrate a velocity function, it gives you the position function. But if you integrate it on a closed interval, so if you take a definite integral of your velocity function, that gives you the displacement of the particle. Right? Not the distance that it travels, but the displacement. So if I integrated from 0 to 7, then that would mean of a velocity function, that would tell me how far the particle moved between t equals 0 and t equals 7. Next thing to remember about all this particle motion stuff is that the absolute value of velocity is equal to speed. So velocity has direction to it, right? If I say that the velocity is positive and we're moving along the x-axis, then that means that it's moving to the right. If I say the velocity is negative and we're moving along the x-axis, we're moving to the left. Positive velocity on the y-axis means up, and negative velocity means down. Speed, though, on the other hand, is the absolute value of velocity. It has no direction. So if my velocity is 5 meters per second, my speed is 5 meters per second. If my velocity is negative 5 meters per second, my speed is positive 5 meters per second. Speed will never be negative. It is always the absolute value of velocity. And because of that, if you take the absolute value of your velocity to get your speed and then integrate that, it will tell you the total distance that something travels on the time interval rather than the displacement, right? Because it could move to the right and to the left, or to the right and to the left, and the total distance traveled would be much greater than the displacement potentially if you had some negative velocities in it. So those are just some of the things I want you guys to think about. We've talked about all those before, but you're going to need all of those ideas to complete some of these problems. Does that all ring a bell a little bit? Sound okay? Feel all right about that? Hopefully so. Hopefully you were listening and not just immediately starting this problem and ignoring everything I said. All right, cool. So for part A, we want to justify why there must be at least one time between 0.3 and 2.8 where the acceleration, or the derivative of the velocity, is equal to 0. So most of the time, if they're going to ask you why the derivative of something must equal a certain value, in this case 0, that's got to do with the mean value theorem for derivatives, right? Because if we remember, and I'll do a sketch here on the next page, the mean value theorem for derivatives says that if I've got a function that's continuous and differentiable on some interval from a to b, the mean value theorem says, that wasn't a very good line, that the average rate of change between those 2 points is the same as the instantaneous rate of change at least one value c that is between a and b. And it just so happens that it might occur, that wasn't very good. It might occur at multiple c values. Okay? So the mean value theorem says the instantaneous rate of change, or the derivative, is equal to the average rate of change, or the slope. Right? That's the mean value theorem. So part A, when it's asking to justify why the derivative must be 0, the first thing we want to check is the average rate of change between 0.3 and 2.8 0? And if we look at the chart, the velocity values are the same, so it must be. So we're going to say 55 minus 55 over 2.8 minus 0.3, as that equals 0. And so by the mean value theorem, the derivative equals 0 somewhere on the interval from 0.3 to 2.8. And if it equals it on the open interval, well, it must therefore also equal it on the closed interval. Does that make sense there for part A? Any questions on part A?
Could you did you have to use MVT for this one to get the point?
No, you didn't specifically. There's other ways you could do it, which I'll talk about here in 1 second. So first off, if you used MVT, you'd get 1 point for showing that this was 0 and 1 point for an explanation using the MVT. There's other things you could do. For example, you could say that the velocity was decreasing from 0.3 to 1.7. So from 0.3 0.3 to 1.7, velocity is decreasing, and from 1.7 to 2.8, velocity is increasing. And if the velocity is decreasing and then the velocity is increasing, then there must be a place where the derivative of velocity, acceleration, or v prime, must change signs. Right? It must change signs somewhere on that interval. And if the acceleration changes signs, then that tells us one of two things. One, that the derivative could equal 0 on that interval, or the derivative could be undefined on that interval. And obviously, we're not going to have an undefined acceleration, but also we know that we couldn't have an undefined derivative on this interval because it says the function is differentiable. So it must be differentiable on that entire interval. So the derivative has to exist everywhere. So you could have gone in and said, because of that, v prime must change signs. So it must equal 0 because it's differentiable. So that's another way you could do it. You could have said that because this was a closed interval, that there had to be an absolute max and there had to be an absolute min on this interval. And you could have shown sort of the same kind of thing, that there must have been an absolute minimum because it went from 55 to 55 at the endpoint. So because it decreased, you knew there was a minimum somewhere in there by the extreme value theorem. That would have worked. Any of these would have worked. So did you show it one of these other ways?
Yes, I was just wondering if you could explain it another way.
Yep, most definitely. So at least 2 or 3 good ways to explain that one. I think on the answer key they did it with mean value theorem, and I think they specifically stated the extreme value theorem. Yeah, which is basically the same thing as what we're saying here. If you didn't say the extreme value theorem, that's fine, but you say there has to be a minimum on this interval, and because the function is differentiable, that minimum must be a place where the derivative is 0. Any other questions there on part A? All right. Part B should have been pretty easy. It says use a trapezoidal sum to approximate the value of the integral from 0 to 2.8 of b sub p. So if we want to use a trapezoidal sum, there's 2 things you can do. One is you can use the formula, right, for the trapezoidal approximation, but you can only use the formula if the subintervals are equal. These subintervals are not all equal between 0 and 2.8. This one is 0.3, this one is 1.4, this one is 1.1. If the subintervals are not equal, then you have to just find the area of each trapezoid, and some of those trapezoids, this one, for example, ends up being a triangle, actually. But you just find the area of each of those little chunks, and then you sum them together. So we will first say that the heights of each trapezoid will be the difference between 0 and 0.3, 0.3 and 1.7, and 1.7 and 2.8. And so as we go through, we'll say the first one should be 0.3, and then it should be 0 plus 55 divided by 2, base 1 plus base 2 divided by 2. And then the next one was was 1.4 for the height. And then 55 plus negative 29 over 2. And then the last one had a height of 1.1 and was negative 29 plus 55, basically the same thing, right, over 2. And you would do all the arithmetic on that, and I think it came out to be 40.75. And that was just worth 1 point for all of part B there. Any questions there? Cool. All right, part C. Part C says we've now got a second particle, particle Q. It's also moving along the x-axis. Its velocity is this nice little function, 45 root t cosine 0.063 t squared meters per hour. We want to find the time interval when the velocity is at least 60. All right, so when is velocity greater than or equal to 60? So basically we're looking for when is 45 root t cosine of 0.063 t squared greater than 60. So we're going to say for part C, we got v sub q of t. We want it to be greater than or equal to 60. So we need to figure out at what time periods v sub q of t is equal to 60, which should be easy enough to do. You can either graph v sub q of t and y equals 60 and look for the intersection points, or you can graph v sub q of t minus 60 and look for the x-intercepts of it, see what is equal to 0. And so that, using your graphing calculator, you should get values of 1.66181 and 3.51917. And getting those two values, I believe, actually, no, not getting those values. That wasn't worth a point yet. So you had to get those two values, and then you had to look at it and say, well, is it from 0 to 1.8, or is it from 1.8 to 3.5, or 3.5 to 4, for which we're actually greater than 60, or when this minus 60 is greater than 0. And we would have discovered that it was between, we'll call this A and B. So we would say that it was v sub q of t is greater than or equal to 60 on the interval from A to B. And that interval, the closed interval, was worth 1 point. You could have written it out in like set notation, right? T is less than or equal to B, greater than or equal to A. That would have been fine. You could even write it out in words if you want to, and that'd be fine. Any questions there on the first part of part C?
So when you're trying to find like the interval, do you look at the graph or do you plug it into the original equation?
I would just look at the graph if it were me. But you can, I mean, you can plug it in and show the values if you want, but I would just look at the graph.
Also, if you're getting calculator values, how many decimal places?
So your final answers need to be rounded to at least 3 decimals always. Okay. You can round it to more than 3 decimals. You can not truncate it at all based on, you can put all 9 decimals that your calculator gives you. That's fine. But I think normally when you look for x-intercepts of something on your calculator, it just gives you 6 decimals by default. So write those out for any calculations that you use and use the full written out value for the calculations. But if you truncate it in the end as 1.866 and 3.519, that's fine. But always 3 or more. Good?
Yeah.
Cool. All right. So the second part of part C says find the distance traveled by particle Q during the interval when the velocity is at least 60. So we want to know the total distance traveled by particle Q on this interval that we just found. So normally when we do a total distance traveled, we do the absolute value of the velocity, right? That's what I was just talking about a few minutes ago. So you would integrate the absolute value of the velocity function from A to B, and you'd get some number. And that's really all you'd have to do for that, which came out to be 106.109 if you rounded it. And that is good enough. Now you might notice that if you forgot the absolute values, you still got the same value. And that's because the absolute value of V of Q on this interval is just equal to V of Q, right? Because the interval, your velocity is always 60 or greater, which is clearly always positive. So the absolute value is redundant. It doesn't really do anything. So if you left off the absolute values there, you're probably okay on this problem. They probably would have still given you the points. But it's really important to recognize that distance traveled has to be absolute value of velocity when you integrate it, because otherwise you're going to get the wrong answer if your velocity is ever negative on that interval. Does that make sense to everybody?
Yes.
Okay, that's very important, and people will make that mistake on the AP test and lose a point or two that they don't need to lose. Yeah. Cool. All right, so that's part C. Any other questions on part C? All right, part D then gives us some more information about particle Q. It says that its initial position at t equals 0 is -90. And then we want to use our answer from part B and our function from part C to approximate the distance between P and Q at time t equals 2.8. So if we want to know the distance between P and Q, we need to know the position of P at 2.8, and we need to know the position of Q at 2.8. And we need to find the difference between them. And since we don't at this moment know which one has a larger value for the position, we'll just take the absolute value of the difference between any two of them. Does that make sense for what we're trying to find? This is what we're trying to find. Position of P at 2.8 minus position of Q at 2.8, absolute value of that. Everybody clear that that's what we're looking for? Okay.
Yes.
Great. So how do we find the position of P at 2.8? Well, we go back and say, oh, we found the position of P at 2.8, right? We approximated the integral from 0 to 2.8, which told us the displacement, right? This was displacement. So for part D, we take the displacement, how far it traveled from 0 to 2.8, and add it to the initial position, which the initial position was 0. So 0 plus our answer from part B, which was 40.75, should be our position of P at 2.8. Everybody good with that? Then we need a position for Q at 2.8. Well, the position of Q at 2.8 ought to be the initial place that Q is at, which is -90, right? That's what it told us here, -90. And then its displacement from 0 to 2.8. And so to find its displacement from 0 to 2.8, that ought to be the integral from 0 to 2.8 of V sub Q of t dt. So initial plus displacement of Q. Everybody good with that?
Yep.
Cool. And then you just use your calculator to find that integral, subtract 90 from it, find the difference, take the absolute value if needed, if this is a negative, and you end up with 5.188 meters is the distance they are apart. And that one, the point breakdown was 1 point for having this integral, 1 point for having the full expression for the position of particle Q, and 1 point for the distance that they were apart. And I think I forgot to give you the, no, I gave you the breakdown for C. This was 1 point for C. Having this integral set up was 1 point, and the final answer was 1 point there for C. Any questions there on any of that question? Everyone's good? Not too bad? Okay. The next one, if you thought this one was bad, the next one actually I think is a little bit easier, so that'd be nice for you. So here is the next one we will take a look at. I'm gonna give you guys 15 minutes to work through it right now. Hopefully all of the talking about the previous one will help.
Mr. Bachelor, sorry to interrupt. I just had a quick question.
Yeah.
Are all of these questions like a distance, speed, velocity questions, are they generally calculator or are they generally not calculator? Or is it a mix of both?
There is a mix of both. Like if I get there, the most recent ones that they've had were calculator, those last couple, but like this one right here is a non-calculator, then a calculator, then a non-calculator. So we'll do some of each.
Okay.
It varies. And some
so
of
the
them.
quiz will probably be like half, so sorry, the quiz will probably be half and half then, right? So like the
Correct.
two. Okay, thank you.
And you're going to see some, we'll get to some like this where they give these really annoying looking graphs. Or, we just did one with a chart. They do a lot with charts. There's another one with a graph. So we'll do plenty of those too. Some weird different ones. So lots of different types. Good question. Yeah, we'll have some of each. So these first two here are calculator. All right, I will give you guys 15 minutes to work through this one right now, and then we will reconvene at that point. Ready, go.